There, I'll use the machines. So part of this, you'll see if you went to Claire's talk today, some of the slides, they're not on a napkin, but it's very similar to what we do. I'm going to talk about some history, design of the compilers. If you haven't heard of this, if you have, just rest for a minute. We'll get to the other stuff. Status of the current compilers, and then I'm going to talk a little bit about things that are issues, the debugger, changes in macro that might be visible to some people, and C++, which is always different. So one of the things, so on Itanium, this is part of the pictures I drew with Claire. So all of our compilers on Itanium, well, minus macro and C++, always different. They talk to our proprietary GEM backend. Every front end talks to the same code generator. GEM generates Itanium code. Picture's essentially the same on Alpha. I just didn't give an Alpha picture. And so they have this. And so we said, Claire says, how are we going to port to VMS? And I'm like, I'll tell the quick story because I think I'm not under NDA anymore. When I worked for Hewlett Packard, this is about 6 months or so before I left HP to go join VSI. I got an email from my manager saying, John, sign this electronic NDA. I signed it, and they go, okay, your manager says now knows you're not going to work for a week. Go off and write a white paper on how you would port the compiler tool chain to VMS x86 if it existed. So I went off and thought about it, and I gave some stuff. Claire and I talked about this after the Itanium port. How would you port it to the next architecture? We talked about in the hallway. What are the easy things? What are the hard things? And I wrote this thing, and I sent it to whomever. I had no idea who asked me for it. I just sent it back to my manager, and then I went back to my normal nonstop compiler work. And then fast forward several months, I'm visiting Claire and Burns Fisher at the famous Panera. I think they've made a plaque there now. And I get there, and the first thing I think Claire does, he has these couple of big envelopes and pulls out an NDA and says, can you sign this? And I sign it, and then I think my memory is you pull out a copy of my email that I wrote. He said, I have some questions. And then the conversation went from there. But so that's a fun story. So there's a 10 course. What will we do to go forward? I said, well, we have several things to do. We can continue with our GEM backend. We have the sources. We can make it better. It's written in Bliss and C, a little bit of C++. But if you want to get to modern x86, Alpha and Itanium were known hardware targets, not a lot of permutations. You remember Camille's talk earlier, how many different AMDs and Intels and microarchitectures and other variants of that have to do. I did not want to be in the back-end business. So let's go pick somebody else's back-end. What we still want to do, though, is pick the right back-end. I'll talk about it in a minute. But how would I do that is, well, it's easy. I would just pick a back-end, in this case, LLVM, and let's convert the GEM intermediate. Let those front ends talk exactly like they used to talk. They still think they're talking to the GEM backend. They make GEM symbol tables. They make GEM intermediate language. They know nothing about LLVM. Double negative. And then we convert it, give it to LLVM, and it generates code and dwarf and everything else. So for the most part, most of those front ends had very few changes to it. I think the Pascal front end, I think I changed maybe 20 lines of code, 50 lines of code at most, and you just rebuilt it. It's all in Bliss, rebuilt it with the Bliss compiler eventually, and it all hooked together. So that's kind of the picture started with. It's evolved a little since then, but that was the original picture. And so how do I make that picture work? So on Itanium, I have to go grab an LLVM, build it on Itanium with the C++ compiler that I have on Itanium, build a Bliss front end, a C front end, link it with that. The G to L's entry point is the same name as the GEM backend entry point. The front end still think they're calling GEM. GEM compile module here. So make all that together, and then I have a magically working Bliss cross compiler, C cross compiler. But how to do that? There are gem intermediate. There's almost 300 different, call them tuples, but opcodes or something that the front end would ask the back end to do. Add this, subtract that, fetch this memory, rotate this. It's essentially think of it as a fancy assembly language for the most part. So how to do that? Most of the things are easy to map, but of course, GEM had a little better type system. It knew about packed decimals. It knew about varying strings. It knew about things passed on by descriptor. LLVM doesn't know any of that. So we had to mention that G to L piece turns a simple, sometimes single gem operator and expands it into 20, 30 LLVM operators, right? Complex numbers in LLVM is just a structure of two fields. There's no complex data type in LLVM. So we had to expand all that. For the most part, it worked okay. If you want to know, only 36,000 lines of C++, and I'm guessing we have a lot of comments. The actual number of code and headers, it might be 30,000 lines of C++. So not too bad. And the only one that surprised me is the difference in how gem and everything on VMS initializes memory. If you're writing a macro program, people are macro programmers, you declare a PSEC, declare a label, and you say, here's my label name, and you say .long this, .byte this. You declare storage with initial values, and the name of that is just a label. LLVM says, nope, variables have names and variables have initializers. Okay, fair enough, but gem was the P6 have initial values, and variables are just places in the PSEC, almost like if you're writing an assembly file, right? So that all seemed easy to do until the day I met the Bliss global bind construct. And so if people don't know Bliss, you can take a variable, a global variable. This is visible to everybody, and say, oh, by the way, this is called A, and in the middle of it is a global variable named B. So it's like a way to do these overlays at a visible to the linker level. I couldn't describe that to LLVM at the time with the cross compiler. So that was the challenge, to be honest. So we had to make things what to do to LLVM. Again, LLVM thinks there's only one pointer size in the system. I knew we're going to have dual pointer sizes, 32, 64s. Our memory model was different. On Linux with LLVM, you have just all sorts of, you either all of your code and static data is all usually just linked in one blob together. We put code in 64-bit space on VMS x86. So it's way up here, or if Drew draws the pictures, way down here. But our stack is still 32-bit. Our static data, we have these, again, everybody wants to love on VMS descriptors and VMS item lists. They are tying your hands into 32-bit pointers. Yes, we have 64-bit descriptors. Yes, we have 64-bit item lists, but we have all this legacy code that's been there for a really long time. Ian's got a whole pile of it that has 32-bit pointers in it. So I got to keep all that data, both the stack, because you might make a descriptor to something on the stack, or your static data. So data is in 32-bit space. The code is way up there. And so that was a model that LLVM says, who would do that? Well, we did that. So there was a handful of changes we made to LLVM to do this stuff. And then a lot of stuff dealing with DORF. We'll talk about the debugger in a minute. GEM and LLVM are very different in how they view DORF. And then we had to worry about some of these libraries that come with C++, because LLVM itself is written in C++. So thinking ahead to be native porting, I had to get all those libraries there. Early on, I didn't need those libraries for the bootstrap. I just needed Bliss C and a macro compiler. So here's kind of what we did. I've talked a little bit about that. We cross-compiled on VMS, but no cross-compiler for C++. Didn't have all those libraries. I couldn't make them work on Itanium. How would I, because the compiler itself was written in C++, but it's Clang, and it was a nightmare to figure that out. And then no BASIC. I'll talk about BASIC in a second. But how we did this, how do you get a C++ compiler or any of this stuff more on the native bootstrapping? I compiled on a Linux machine today. So I have a Linux hosted C++ compiler, Clang based, but it has VMS isms baked into it. So I have a cross compiler from Linux x86 to VMS x86. So it knows about some of those memory model changes I just talked about, that you have to put code here and data here. But it's running on Linux, but it has to know things like what are the names of the CRTL routines on VMS, not printf that's on the Linux box, but $, printf, tx, whatever they are on the VMS box. So this cross compiler is a kind of weird beast. But we built all that. Right. And then how I'm getting the native compilers today, cross-compiled that gem, the Clang, moved all the objects over, put them in a bag, drag them to VMS, link them together. Then I have a C++ on all those libraries. The very first ones, I use the same cross-compilers. To most of our compilers are either written in Bliss or C. I use the Bliss and C cross-compilers, compile the compilers. And so now I have object files that have x86 instructions in them for the very first time for the compilers, link them all together with all those LLVM backends, and I have a first generation compiler. Of course, they were built by cross compilers, no optimization. So these very first generation compilers were big and unoptimized themselves, but could generate optimized code. My next step is I build the compilers with the compilers. And so now I have compilers smaller because they're now optimized that generate optimized code. And of course, then I have to generate and run test system after test system to make sure as I do that, I don't change the behavior. Right? I don't want the optimizer to break things. And we did find that. There were times where we built these compilers. Then you use those compilers to build yourself again to make sure you didn't introduce another bug in the compiler with a bad optimizer. And yes, those happen too. And so we're almost done. I think Claire asked me once, so on the scale of 1 to 10, how much optimizations are in these compilers? I'll go with 8, 8.5. There are some things that you can tell additionally to LLVM about, like pointer aliasing, that C and GEM know about on Alpha Titanium. We don't share that information with LLVM yet. As part of this whole GDL process, the representation is different, how GEM wanted it and how LLVM wanted it, but it's on the list. One of those things for 9.2.4 or something, we'll probably tweak it again. But for the code that comes out now, I'm pretty reasonable with it. And if you compare image size, again, somebody asked image size earlier, image sizes on x86, pretty big. But remember, XEs are full of not just code, they're full of debug information, unlined information, strings, all sorts of stuff. When you run an XE, the image actor doesn't read that whole XE in the memory, it reads a part of it. Sometimes a pretty small part of it. So you have a 100,000 block XE file and you run it, we might read 10,000 blocks. So don't get confused by image size. So that's kind of how we got to where we are today. So we got native compilers. 9.2.3 does not have cross tools anymore. All those previous versions of VMS had a cross tools kit. We don't ship them anymore. If you have to use the native compilers. I've got them all now. We still use them internally, but we don't give them to anybody else. Because they generate unoptimized code. Why would you want to do that? So here's a quick boring table. Most of the stuff is going to be easy. The one thing I want to point out for all these new versions coming up, most of them are happening almost immediately. I think the Pascal one and the COBOL one, while we're sitting here now, my Magic Elves are sliding a new COBOL into the portal, I think this afternoon. I think the Pascal one is there as well. And the rest are churning out. I mean, Camille in his futures talk, his little pseudo-light roadmap, talked about a refresh sometime next year or so. That's to pick up a better LLVM. But for picking up newer versions, bug fixes.
Already there per se.
Yeah, so we're spitting them out as while we're here. I'm trying to, I'm distracting you, and we're getting the powers there. And there's a basic one.
Like a cadence where we release updated compilers about once a year to pick up bug fixes, but also to keep like up with the current standard of LLVM.
Yeah, and especially picking up a newer LLVM, like you mentioned, there's things like the stack smashing and other things that are not even in the LLVM version 10 that we're using for these native compilers. I need a better LLVM to pick up that better, those security features that you can get today in Clang on Linux or that type of stuff. So yeah, we're wanting to keep, we made that mistake, I won't say mistake, but on Itanium, we picked up the C++ compiler there, we picked up an older Intel backend, and we got stuck with that forever. And then Gem, it got stale. Well, half the time we sold most of the Gem team off to Intel. It got stale as well. So somebody asked me once, why don't we use every single feature in the Itanium backend? Was it you, Drew, that asked me that? It's like, because we didn't have anything to do with it. The big thing is most of these bug fixes are debug related. You may have noticed, we'll talk about that, but the debugging experience on 9.2, 9.2.1, 9.2.2, abysmal. I know that. And every time it's a little better, and it's a little better as in, well, it may not fail immediately, but it's probably going to fail in the next 5 minutes.
I installed the latest debugger.
Yeah.
It became worse.
Okay.
Sure, I initially didn't do what I wanted.
Yes.
And after the update,
Yes.
it just crashed immediately.
And so the one in V923, I think, is going to be better, but yes, let's just.
So, what if I'm not installing 9.3 and stay on 9.3?
Yeah, we should make another debug update kit for that'll reinstall on 9.2.2 with this better debugger. Now that Tim has it.
By the end of the year?
I'm not going to give you a date, but I think that's a reasonable request, and I think we can probably turn that around within a reasonable time period. Obviously, getting those things built and tested. Right now, I think our testing group is a little busy testing 9.2.3, the real one. So yeah, I have to get all that scheduled. I mean, certainly for a hot fix, I can probably build one and give it to you under the table, totally untested. You may say, hey, I'll give it a shot, because the worst that can happen is to use my current debugger, which immediately crashes. I can't break it any more than it is, right? It's already broken. We can talk about the T-bit one. Yes, that's so most it's here. So it's almost all debug support. The big one that's now getting debugged. So 9.2.3, there's a new version of native macro bundled with the system. It finally now has debug support in it. So you can get source line debugging in macro if people who want to do that. You can examine R2, R3, R4, R5. You can do, and it's just like it was on Itanium. But you were about to say something?
No, I'm just going.
Okay.
I'm still trying to wrap my head around that macro is now a compiler.
It always has been since alpha days, right?
I know. I'm still
okay.
trying to wrap my head around that.
Oh, okay. Okay. Oh, that's it's an Escher drawing, yeah. And the fact that, of course, that macro is partially written in macro, but the C compiler is written in C. So this whole recursive argument is
Most of DCL is still macro.
There's a lot of things still macro. No.
Yeah.
So I want to talk a little about the debugger a little more. So the debugger on Itanium reads dwarf, but it was Gem on Itanium. It generates dwarf 2. The standard is, the current version is like dwarf 5. It does dwarf 2, a little bit of dwarf 3, and that's all the debugger claimed and knew. And the debugger people would tell you, we are dwarf 2 compatible. The answer is no, they weren't. What they were compatible with is the dwarf that Gem generated. They got really used to what Gem said. And so dwarf is this collection of the A in dwarf doesn't stand for arbitrary, but I like to call it arbitrary. There's all you can do as much or as little as you want, and the debugger is supposed to just figure it out. Well, our debugger loved what Gem did, and if you told it anything else in any other form, it just, I don't care. It would just walk away from you. And the answer is, no, you need to be prepared for almost anything from the dwarf standards that the compiler can throw at you. And so now LLVM generates, we asked for dwarf 4. It's like, it's generating all sorts of new tags. The debugger should just say, thanks for telling me, not interested, but good. But right now, the debugger, the moment it sees something it doesn't, or at the moment it saw something it didn't like, it just says, I'm done. It would stop reading every dwarf in the file. So it wouldn't get routine names, it wouldn't get variable names, it would get nothing. Now, we've caught up for the most part with that. So the debugger now, 923, reads correct about all the tags, except for C++. We'll talk about C++ in a minute. It's always different. And then the issue we still have today that we just got to fix, I think the reason it crashed for you is when you in the debugger and you step into a routine, let's think by instruction level, you're now in the first instruction level routine, the debugger wants to know, well, who called me? There's this in the prologue, the calling standard routines have a hard time finding where the saved address is until the prologue is finished. You have to set the frame pointer and all sorts of stuff like that. So the debugger was very confused on when it was in the middle of prologue routine, the whole step into thing, that it just would say, it would crash. It would just confuse the debugger and act failed. So if the workaround is to set a breakpoint on the first line of your code, if you say, set a breakpoint on the first user statement in your Fortran program or your C program and do a go, you'll get right to the statement. But if you're trying to step into a program, you got really confused. But I think we fixed that now. But it's well, not yet, but hopefully we'll fix it for you. So that's kind of where we were at the debugger. Two things. We had a hard time figuring out where we were in the code, and we didn't read all the dwarf correctly. Sounds like a perfectly good broken debugger to me. It really did. It worked on some things. You can see the source code finally, but you really couldn't do much with it. So that's the debugger. One thing I want to talk about, I want to talk macro a little bit. We talked about that picture you saw. All the other compilers go through this G to L and into LLVM, high level language. It gets all the optimizers. Macro has always been different. And the difference really for macro, we'll talk about the registers in a second, is that in a macro program, you can do things like jump from middle of one routine into the middle of another routine. Can't do that in any other language. You can't do that in C. We'll set you up long jump, but that's just going to hurt your head to do that everywhere. It's like you can have, and there's pieces of code on the system. Rob knows the shadow driver. It's a huge piece of macro routine. And we did some analysis. The compiler looked, every entry point in that module could eventually get to any exit point. We couldn't tell at compile time where you're going to come in, where you're going to leave. So I had to be prepared for all that. This entry point, it's like if you're used to Fortran and entry statements, multiple entries into a Fortran program. It's abysmal. So that's why macro is always different. I have to remember that. I have to remember things like condition codes. I have to remember things like, sharing implicitly registers from one routine to the next. It's this magic state that goes from routine to routine. So when we went to do macro for x86, you have 32, even though it's VAX macro, 0 through register 15, alpha allowed you to access the alpha registers, register 16 through 31 in your MAR file. We supported that on alpha, supported that on titanium. Said, okay, John, how do you access 32 registers on a machine that has 16 at best? Many of them have dedicated meanings. How do you put 32 registers into 11, 10, 9? You can't. We can't. We tried. We tried several things, including, again, alcohol, as much as we could.
That's Jim. No mouse pad.
No, there's no mapping. There's no mouse pad. There's no mouse pad. I could have made you a mouse pad. The answer is every one of these registers are mapped to a memory location.
That is the one thing I reminded Claire he fell down on.
No mouse pad. I should have put that on here. Where's my mouse pad?
Very first VSI where we said we are going to port the x86, that there will be a new mouse pad.
Yes.
I wanted to buy the mouse pad.
I know.
And then we figured out we didn't know how to do it.
Yes. We couldn't. Now, some people, I didn't mention here, if you've been following along with all those new additions to the Intel architecture, like I said, they seem to churn one out, a new ISA edition every week. There's one, I forget the official name about extensions. They've added another prefix byte to the instruction stream so you can access, they're actually adding another 16 registers. It'll be up to 32 registers in the architecture, I don't think they've made a chip yet that implements that. And if it is, it's not a Gen 10 or Gen 11 machine. It'll be a Gen 13, 14, 15 machine. I have no idea. So the code that we generate with LLVM today, I should mention, it's just straightforward, boring x86 code. I do a few things that are maybe newer instructions, not in the base, Intel 4004 instruction set, but I've got some somewhat newer, but I don't do any, you're not going to see any, parallel instructions that touch YMM or ZMM registers, or things are these 512-bit registers. Yeah, we don't touch them right now because I don't know if all the machines have them or not, right? I'm not going to bury that into the operating system just to make sure that I would require that on every machine that booted the system. I don't know if every hypervisor supports all of those. So I said, I'll just stick with the stuff I know, and we'll think about that later. It's no different than if you would try to generate on Alpha some of those EV56, some of those byte and word instructions, and take that back to an older Alpha machine, like an EV4, EV5. It won't work. Well, we have some emulation in the operating system that's kind of confuses things.
I still want my mouse pad.
Okay, I'll make you a mouse pad. So we have that, but we had to teach. So we make memory locations. So every time you touch a addle R2, R3, R4, we fetch from memory, we do the add, store it back. John, that's a lot of memory stores. Somebody's got to know. We had to put the stuff in there. But the answer is, my story is, every x86 box on the planet, I don't care if it's running Linux or Windows, has the same limited register set that we do. And go write yourself a C routine on a Linux box, compile GCC, fast, the best code you can get. All of the variables are on the stack. They fetch them, they do things with them, put them back to the stack. The x86 machines live by the stack, and that means they live by cache. Somebody's talking about the fastest chips and how fast. Norm was talking about how fast you get clock speed on Intel chips. Look at the Intel price sheet for chips. The expensive ones have the most cache, not the fastest clock speed. So the idea is, we're going to be touching all these locations over and over and over again. They're in the cache. They better be in the cache. But they better be in the cache on your Linux box or your Windows box, or those systems would be miserably slow. So I figure, why not? Be a lemming, follow the path. And so I haven't had a problem with the perceived performance. But if you start looking at the generated code, and if you're a nerdy person, you're going to see us at the top of every macro routine, get a pointer to these pseudo registers, and we're reading, writing. Now, I think we can optimize that slightly. If I'm seeing the same register touched more than once and not written back, I can only fetch it and not have to store it back. But it's hard. There's only so many registers I can do with, because it's not like on Alpha or Titanium or Alpha where there's all these preserved sets across the code. So we did all that. I did want to point out that macro also, if you look, the calling standard says all return values go in the RACS register, real hardware register. So I got to put every return value in RACS, because I can be called from the C routine. They expect the result to go back in RACS. But I can be called from another macro routine who calls me, does a JSB or a call S to me, and expects the result in R0. That's the pseudo register R0, the thing in memory. So I got to do it twice. So if you look at the macro code, please don't. You'll see a lot of stuff that's shuffled around. Trust me, there's a reason for most of it. And then the big thing I want to talk about, though, is C++. Yeah?
Let's do the same thing. Puts it in R0 as well as.
No, not unless you have a special linkage in Bliss. You can do it that way. But no, by default, all the other commanders just leave things in racks. Yeah, no, I'll take that back. No, I think if I call S a Bliss routine from macro, I do expect it to be in R0. I do think maybe we put them in both. If you have a linkage declaration, we will. So I think if you don't have a linkage, we won't. But I think also for macro, I'll take that back. So how it works is, I'm refresh in macro, after I do a call instruction and it comes back, macro moves racks into R0. And then you can touch R0 and use it. Now, of course, if no one ever touches R0, let's say you don't check the status of your routines, one, shame on you. But if you don't, maybe I can avoid that store. But again, I'm storing into memory that's in cache. So again, I don't know. So C++. If you haven't noticed, it's different. So the C++ we had in Itanium was only C++ 03 compliant, and barely. I think it still had bugs in it. But people now want more than that. A lot more than that, right? C++ 11, 14, 17, 20, 21, there's 22. At some point, don't worry, the language will collapse under its own weight. The latest standard is huge. A C++ standards meeting, I think like 200, 300 people show up, and they have like a big plenary at the beginning and talk about, then they break up into people that do headers and this and that. I don't know if any one person understands the whole language, which is a bad sign to me, right? It can't be good.
The amount of progress is inversely proportional to the number of participants.
Yeah, it sounds. And then also that Itanium compiler was based on an EDG front end, Edison Design Group. They're in New Jersey, and it had an Intel-based back end. None of the licenses would work for us. We couldn't take it anywhere. Even if we wanted to, I would take an old C++ compiler forward, and I couldn't find any standard template library. The one we use in Itanium has a license that doesn't let me take it to x86. I was stuck. But hey, guess what? LLVM comes with its own C++ front end. Plus, I'll need it to build itself. Like I said, the EDG compiler would never come close to compiling the C++ sources inside of Clang and the sources inside of LLVM. They need like C++ 11 for 14 even just to compile them. So I need a newer C++, make everybody happy. Let's go take the Clang compiler, bring it to VMS. Just like we did on Itanium, we took a Linux Itanium compiler from Intel, brought it to VMS, and taught it about dual-size pointers, taught it about pragmas, taught it about listing files, taught it about including from text libraries. I know the list. We get to do it again on a front end we've never seen before. So we just dive in and start working on it. So, but one of the things that comes on that I also being pressured, I don't think Brett's in here. People for years have said, John, on VMS, the size of long is still 32 bits, just like it was on VAX. Why? On a 64-bit Linux box, int is 32 bits, long is 64 bits. And if long 64 bits, then size T and pointer diff T on a Linux 64-bit system is 64 bits. VMS has been different from the beginning. They did this as a better recompile and go going forward from VAX to alpha, and they have stuck with that forever, partly because they didn't want to ask people to be different, partly because they were afraid they're going to break things. I think both are true.
John, on page
Mm-hmm.
of VMS on Itanium, because it will continue trying to shove pointers into long size T.
Yes. Now there is an int pointer T type in the standard that actually is 64 bits, but no one uses it. People I've seen either size T or offset T as the name of the type that can hold any pointer. That's not what those are, but it happens everywhere, including that one. It's like, I got to do this. So we're going to make everything be 64 bits. Pointers on VMS on all the other languages, they're 32 bits. If you want a 64-bit pointer, you have to ask, and you have to call special routines to get 64-bit memory. Nope. On a Linux box, you call malloc or you call new, you get 64 bits back. And on something that needs a lot of memory, you want 64-bit heap to be used. I said, we're going to keep all of that. Now, my team at first, internally, we were pretty hard-assed about it. We said, we're going to just, there's 64 bits, that's it, no choice. Until I introduced them to item lists and descriptors. I said, we need 32-bit pointers because I have to be able to describe these things and put them in that. And if you think about that, I can't just start randomly putting mallocs and news in 64-bit heap because I got to be able to jam that address into a 32-bit descriptor. Half of a 64-bit address is usually not very good. So if you ever see, then of course when we fits the 32-bit, somebody's going to sign extended. So you get all those Fs at the top. So we had to do that, but then I said, okay, We do have to give the ability to go back to 32-bit pointers if you want them. So all those pragmas that you see in C and C++ and Titanium, pointer size, put them all in. Command line option, put it all in. Now you can set it to be at the command line. You can say pointer size 32 and put it back to like it did on Titanium if you're really desperate for that. But we have left everything 64 bits by default. Names, we don't uppercase names by default. If you want it, you can ask for it. But on Linux, no one uppercases a name. Let's leave it at that. And so I'm taking the sense that, by God, you wanted Linux behavior. It's what you get. Hope you like it. So, we've done a lot of things. It's better. You can control it. The only one that's still stuck is long is still 64 bits. You cannot change that. And so we had, matter of fact, the latest Deck Windows kit. Deck Windows, there were places it used long when it really meant int. They wanted a 32-bit thing. They said long. Well, guess what? When you compile those headers with C, you get 32-bit long. You get 32-bit things in a field and a structure. You compile the same headers with C++, you get 64-bit things. And so up until recently, you could not use C++ in Deck Windows. The headers just didn't match. So I think we've got all that sorted by now. So the only two things really that are left, we've added in this listing files. We'll talk about that in a second as well. But the things we still haven't added, and this is where I'm going to show of hands, but I don't know if I trust you people, is we don't have, so global new and delete. There's a feature in the C++ standard where I can just override new and delete for everybody. On a Linux box, it uses symbol preemption to override the new and delete inside the C++ libraries. You can define Linux, you can define your own version of new, and it's not that your code just uses your new version too. Everybody that calls new, even in every library, libc++.so calls your new. So you as a program can override the new call in somebody else's library. But
yeah, so it's more complicated than that.
Yes, it is.
Yeah.
Yes, it is. And it does have also a little bit of a security issue involved. So you have to be careful where you let, so we right now don't have that. And at some point we had it on Titanium, but there's a lot of additional code in the standard template libraries to make that all work correctly. We haven't done it because the standard template library we use is the one we get from LLVM. I don't want to touch code I don't have to. I don't own it. I can keep adding to it, but once I touch it, I kind of have to keep retouching it because I can't touch it and keep it forever. I've got to upgrade to new versions, right? So I handed it, and there's no VAX floating support in this compiler. Anybody care about VAX floating in C++?
On x86?
Yeah. No, please say no. Please say no.
Yeah.
I mean, it's been default IEEE on Titanium. So I'm not doing that. Though I believe if with enough thought and design, I think I can write a C++ class that almost emulates all of VAX code. You can do it in C++, I think. Exercise left to the user. Right? Yeah. But all the other compilers have VAX float. And one of the early things with Claire, we talked about once, I said, I don't want to do VAX floating. That didn't last long. I also said at the beginning, I remember saying, I don't want to do basic.
Oh.
Yeah, and I got some of this. The reason I said basic so long, the basic compiler generates, it cheats, it touches fields in gem that we didn't think it touched, and it has these very elaborate data structures that have to be initialized by the compiler and then passed between the RTL back and forth. And remember I told you how static data different is. It turns out that I did initialize the data layout was wrong. I never can get it right. It took us a long time to get it right. And then I did want to talk about the compiler features. Go ahead.
I saw something on the slide that the order of initialization and the gem languages is different from C++. So does that mean that I will not be calling out to a gem language from C++?
No, you can. You can. I got it. It all works.
I mean, there's a very specific order in which C++ does its initialization. Is it?
There's so yes. Besides this traditional lib $, initialize that you're used to on VMS, there's support for .init array and Just, I got, there's CTORs and DTORs that Clang generates that also were put into the system. I think I got the order right.
Okay, all right, but it's also, and it's deterministic, so.
Yes, it is deterministic.
Okay.
Yes,
As long as it's deterministic.
it is. But yes, I don't, maybe I don't document it. You're now, you're sealed to secrecy.
Because I want to call my basic
You can.
assumptions from my C++.
You can. You can. You shouldn't, but you can. So some of the things we're thinking about, some things maybe in the short term, in the next 6 months, 12 months, some things even longer. I don't know. We talked about a little bit, long double. How many people here use long double? Anybody care? Long double? Long double doesn't work in the current compilers, any of them, right? And the reason is LOVM 342 cross compilers knew about F32 bits, F64 bits, and F80 bits. Those are the three hardware floating types on x86. They didn't know anything about 128-bit floating types, the X floats that you're used to from IEEE. LOVM 10 now knows about more than that, knows about F32, F64, F80, and F128. And you can even ask Clang now to put a 80-bit float in a 128-bit container. You can kind of get mix and match and do anything you want. But I now need to get real 128-bit floating point, cross compilers won't do. So I need native compilers to do that. So the native C compiler that has just gone on the system, on the portal, you can compile things with long double in now, today, brand new. 128-bit, you can have an LL long double constant, and we will parse it correctly, and you'll get the right constant in your code. Don't try to print it out. You know why? Guess what? All the libraries that are on 923 are still cross-compiled. So the CRTL, when you call printf and you give it the percent to print a long double, it doesn't know about it. You try to do a square root of a long double, the math library built with cross compilers doesn't know about it. So part of this long double is this whole bootstrapping thing. I'm having to bootstrap my way along, and at some point when the system's fully native built, it just magically will work. But in the meantime, do we have to mix and match pieces of stuff to get half? And I am not going to ask Bob Wilson, this, our builder, at least without a support or bullies between me and him to how would you build a system with pieces that are native built and cross built all mixed together? It's hard. So that a little bit more optimization, more like I said, more debugger support. The debugger also knows a lot about C++ syntax, or it should. You can set at the debugger and do a set a breakpoint on. You'd like to say set break on namespace : routine name. You can't even do that today on Itanium. That debugger today doesn't even know anything about namespaces, even though the compiler tries to tell it in the dwarf. It tells it all the namespaces it is. The debugger doesn't look. We're fixing that in the debugger. I don't know about any newer debugger syntax. Anybody that are C++ programmers, how do you set a breakpoint on a Lambda? How do you evaluate those things? I don't know. The cute thing on a Linux machine and Clang, they get the LLDB debugger. When you give it the big C++ expression, it doesn't parse that at all. It jits it. It calls the JIT from Clang and jits it and then calls it. But we can't do that yet. Machine code listing, we're still relying on analyzed object DISA to get machine code, and you get just code, not static data. I don't know what to. We have several approaches. Do I take a big hammer and pound that into the LLVM backend to write both an object and a listing file at the same time? I think I can do it with a abstract class on top of the streamers and have two streamers at both and have both an object file and S file in progress at the same time. I don't know. Or add more metadata to the object file and make analyzed object DISA smarter. I don't know. Haven't decided it. Refresh LLVM, like I said, that gives me the stack smashing. It gives me better optimization. They're always tweaking something. Every time there's a new microarchitecture of a chip, they add something to it. You want XMM support, YMM support, ZMM support. You will be able to get all of that now in LLVM 19. And trust me, they change those numbers so fast. By the time we do it, it'll be up to 21, 22, 23. I don't know. Whatever LLVM du jour is, they rotate their numbers very quickly. Like, every time we do like an update kit, they would just change the big number. They don't. C. And the bottom two is a couple even farther out. We don't have really good support for thread local symbols. But GCC and Clang, again, if you want to have a variable that's local to your thread, there is syntax in those compilers to do that. It's not in any standard, but we know there's standards and there's de facto standards. And the de facto standard is, I've already seen code that wants to use the GCC style thread local symbol support. Clang accepts it. You can do it today, compile the compiler today, you can compile it. It'll ask for relocations and our linker will say unsupported relocation. And then you're done. You have nothing left to do. And that's a rather complicated thing. That's not just the compiler or even pthreads. It's the compiler, the linker, the librarian, the debugger, traceback, SDA, I don't know, probably 4 or 5 more. But I don't think I can avoid that for too long. For years, we ignored thread local symbols. Yeah, who cares? That's a unistic thing. We're VMS, we're different. I don't know if I can be different anymore. I'm always different, but that's. And then LLVM comes with a bunch of tooling that goes with it. You can one of the cute things about LLVM that GEM can't do is you can, at any time in the compiler tool chain, you can write out these binary bitcode files. So you can take a front end, have it generate a bitcode file. It's like a pre-chewed piece of the compiler. It's like this, but it's the internal representation, and you can take it somewhere else and feed it back into LLVM somewhere else.
Did we start that way doing that?
Yeah. That's actually how early on we tested. We had our front ends hooked to this G to L. We generated the bit code, copied it over to a Linux box, fed it through the LLVM on the Linux to get an O file, and then we linked it and ran it. The other thing that we can do, I didn't mention here, so on Itanium, our linker there says you've got to be a VMS object file. We check the header, and if you're not VMS, the linker, we're done. Here, I asked the linker person, I said, I want to be able to take a Linux object, bring it to VMS and link it. You can now. Go today to your Linux box and compile, do a -C, get yourself a foo.o, bring it to VMS. The linker will take it. It might give you an info message or two, and it might say, hey, you're calling printf. I don't know about printf. I know about $C printf, TX uppercase. But if you write some jacket routines, and we did that as well. We wrote a bunch of jacket routines the other way that ran on Linux that the name was uppercase $C printf TX. It just called printf. So we compiled a bunch of programs, took them over to Linux, linked them with all these little jacket routines and ran them. We were doing not thousands, but hundreds and hundreds of tests long before we booted the operating system. I did that both with Bliss, Macro, and C. Did them all. So, but LLVM has these additional sanitizers. If you're an LLVM fanatic, there's memory sanitizers, address sanitizers. It's help look for heap overflows and touching things that, pointers that are stale. They have that now. We'd have to put that back in. It requires some RTL changes to do that. But I want to do that because I think they're very useful. It helps find additional bugs in programs. So, and if I do it right, it's not just for, but on Linux, that's the Clang part of it. That's a C++ solution. If I do it right, you can do that for BASIC. Or can I? Right? I don't know how to do that. And I'm not sure exactly how to do stack smashing in macro, since you get to do almost anything you want. But yeah, so. But that's kind of but the biggest thing I want to do is I think the missing machine code is a problem for some people, or no? Do you care? You get the code, you get line numbers, you kind of get, we now get the correct listing line numbers that matches the listing file. Early on, there were source line numbers. We've got all that straightened out. But if you want to see what the static data looks like, if you look at your machine code listing on Alpha Itanium, besides your code, you get to see symbolization of the code. You're touching variable foo, you see the name foo in the code. Here, it's like you get to touch, -48 off some frame pointer register. Well, what is that? You'd like to, maybe that's symbolization? Maybe use the debugger for that. I don't know. But you got the static data. You'd like to see your static data allocated and the names on it. Do I need that? I would like that personally. I'd like to see that. But So those are probably the things, the refreshing the OVM and the machine code and the debugger are probably, if I was going to guess what I'd be focused on in the next year, it's probably that. Unless again, if people tell me different, send me email. Write your request on the back of a $100 bill, send it to me. Okay, any questions? I think that's the end of my, yes. Okay. Woo!
On the patio, residential suite, 6th floor, beautiful view. John will be there to continue his comedy, his other comedy, the team. Everyone is invited.
How do we get to the 6th floor without a card that gets us to the 6th floor? It does? Okay, okay. Oh, okay. Because I'm slumming on the 2nd floor. They won't let me up to the top floor. That's where the big rollers go. So I think Jim was next and Jim. Oh. Okay. 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 Elevator. Well, you don't, since you're not saying, you need a card to enable the buttons on the elevator. But once you get the buttons enabled, any of the buttons will work. It's not like they're keyed to the card for the floor you're in.
So you have to be nice to
Well, I mean, spread the word.
Yes.
I'll go down and get you.
We'll find it. We'll hook you up. Yes, sir.
I remember seeing something in the C76 release notes specifically for the optimizer, saying that there was some optimization there, but not a whole lot, so.
Some of that might be a little stale wording in those releases. I try to clean them up, but yeah. I think I was more referring to is that we're missing all that pointer analysis stuff.
Okay.
So again, C on alpha and titanium and gem, a store into a pointer to an integer, the compiler knows it can't possibly affect a pointer to a float that's on the heap, so it optimizes a little better. I tried to write some benchmarks to see what's the difference, but now I'm still comparing one architecture to the other. I'm trying to compare Clang versus C versus whatever. So
Is the C optimizer for 7.6 at the 8.5 level that you just described, or was a little less?
again, they wrote dot spec the 8.5 level. Yes, I think so. Yeah, and for much code, I think it's really better than that. I think if you have a piece of code, a bunch of nested loops that do pointer accesses and stuff, you might, if you compile it with Clang. And by the way, the Clang compiler has both the DCL interface. We added that, but you can also, we've left it. There's another. We actually, when you install the C++ kit, you actually get two compilers in one. Well, I actually get two compilers separate, not in one image. Two compilers. One has the Linux command line, the real live Linux Clang command line, with all, last time I counted, somewhere close to 600 command line options on it. And you can compile it. Now, I have not tested any of those. I have no idea. You can turn things on. I mean, we require pick code. We require frame pointers. If you want to compile with that command line and turn all that off, God bless you, but I don't know what's going to work.
I don't even know about that.
We have that. So if you wanted, you can do that as well. And so you can turn on features that I haven't tested. But yes.
Okay.
But that's in the release notes too. We actually describe that in the release notes.
The reason I ask is because stuff that I've done,
Yes.
VMS on bare metal work.
Yeah.
There are 3 VMS device drivers out there, and they all natively compile under 7.5.
Okay.
And the first thing that's on my list when I get home is to upgrade that machine to 7.6 and see if
that helps. If not, let me know. Okay. Okay.
But actually, if I'm lucky and the gods continue to smile on me, come on over to my train layout at the dinner tonight. And
Okay.
you can see what the compiler is doing.
Okay.
Everything that's running there is natively compiled.
Don't threaten me with a good time.
And it's multi-threaded.
Oh, all
And
right.
it uses pthreads.
John, I just want to publicly thank you for the release notes to Pascal.
that have been written recently. I don't know if you were the main author or if.
I write almost all the release notes.
The sections on data alignment in particular.
Oh, that thing I wrote years ago, that's still very useful.
I've been under so many.
No, that record alignment guide has been there for years.
Still,
Okay,
that cleared up a lot for me. And-
yes,
And,
yes.
we're actually.
Especially for people back on Itanium where alignment faults were horrible.
Yeah.
Alignment faults on Itanium is thousands of instructions to fix up, including a mode change. Don't do alignment faults on Itanium. No, I mean, it handles unaligned data very well now, and even x86, the instruction set handles unaligned data really. The only one, there's a few instructions in x86 for saving floating registers in memory require an aligned target. But I mean, it's a handful. Most x86 instructions, at least the ones we generate, don't care. Integer on any byte boundary, it doesn't care. It does the right thing. It's a byte granular machine. Unlike alpha early on, we can only do the long store long, and if you wanted to touch a byte in the middle of a long word, you got to do it in a piece, and you got to worry about if somebody else touching the byte next to you. You still have to worry about that on alpha. But Itanium's byte granular in x86 background. And we did some tests. Camille and I wrote some tests. It's pretty good. You're about to clap me out of here. Bring me out. Bring me out.
I think, like,